Okay, we've got a working generator. I've used it to make two test suites. One has 100 puzzles, took about 40 seconds to generate, and the other has 1,000 puzzles and took 10 times longer, nearly 7 minutes. I've put both test suites into the repo. Now, because we used a brute force solver to make these puzzles, not a lot of them are going to be usable. The difficulty is going to be all over the map. Now, the ratio of usable to unusable puzzles varies from puzzle variety to puzzle variety. I believe for these minesweeper puzzles, about 20% of them will be usable, and the remainder will be too hard or tedious for humans. Now, the next step is to modify our generator to be able to identify the easy and hard puzzles. OR Tools provides almost no help in this regard, but it does have one useful metric. It keeps track of the number of branches taken during the solve process. After its solve function returns, you can ask it for the number of branches. I've modified my solver to keep track of this information and return it. A branch is like a guess. It corresponds to a node in the solve tree where the solver is aware that there are multiple choices. Think about how the solve works. It makes a series of easy deductions, and then it hits points where there's two or more choices that seem equally likely. Here, the search tree branches. It picks a choice randomly, goes down one path, maybe that doesn't pan out, so it comes back up the tree and tries the next branch. Each time it does this, it increments a branch counter. There is a very loose correlation between branch count and human difficulty. Very loose, but it's there. Branch count is a very crude yardstick for measuring difficulty. There are intractable puzzles with 0 branch counts, and there are easy puzzles with high branch counts. But branch count is pretty much all we have to work with until we write a better solver. Now, the measured branch count will change from solve to solve depending on the solver order. You can control that by seeding the random number generator on the solver. You'll get consistent branch counts if you seed the solver's random number generator with the same number, and you'll get different branch counts otherwise. You can average randomized branch counts over multiple solves to get a very slightly more accurate bad yardstick. For humans, puzzle difficulty is not a constant objective thing. The same human may find the same puzzle harder or easier depending on the solve order that they take on the puzzle, the time of day, how much coffee they've had, etc. For the 1,000 puzzle test suite, I found only 20% of the minesweeper sudoku puzzles are suitable for humans. Of the puzzles that have an average branch count below 10, most of which have a branch count of 0, about 30% are suitable for humans. So your odds of encountering an easier puzzle are higher with a low branch count, but still not great. Now, if the branch count is over 100, only about 4% of those puzzles are decent for humans. Some of them are easy, but not as many. So let's avoid those for now. About half the puzzles in the test suite have non-zero branch counts. I've included the branch counts in the puzzle comments in the test suite as ABC, standing for average branch count. It's a measurement of average branch count over 5 solves. At any rate, we're approaching a point where we want the computer to solve the puzzles in a more human-like way. To do that, we need to solve several of the puzzles manually and make a record of the different techniques we use so we can express them in code. And to do that, we need to be able to see or print the puzzles. So let's ID the ones we want and make pictures of them. I'll start by looking at puzzles with very low branch counts just to give us 10% better odds of finding tractable puzzles. Okay, so puzzle number 2 looks like it might be an easy one. I have a 30% chance. Also these other puzzles. I'll want to print a handful of these low branch count puzzles and try to solve them with a pencil. So now we need a drawing function so we can visualize the puzzles, print them out, or solve them in Photoshop or whatever. I've vibe coded a few puzzle renderers, and you can usually get 90% of the way there. You might have to tweak font centering and things like that. Here's a render of puzzle number 2, and here's the code that drew it. Basically, you work out the grid size and cell size. You shade any cells you want to highlight, then you draw the grid so the grid isn't covered by the highlights. You draw the clues, and optionally you draw the answer or partial answer. When I'm debugging a solver, I might draw more stuff like solving annotations, especially helpful for spatial reasoning puzzles like tracks. I render puzzles in different ways and use different graphics libraries depending on the needs. Usually the first renders are quick ones, like this one, so I can try out the puzzles. This is a PNG file, a raster format. Eventually, if I'm going to publish the puzzle, I'm going to want to make vector versions so they look good in print. I'll be making PDF files for people to download and possibly for book interiors if I'm going to self-publish a book or two. I mostly don't embed PNG images in my PDF files. Raster images need to be super high resolution for print, and at those sizes they get needlessly big and they bloat the size of the PDF file. So it's better if I can provide vector graphics instructions for the PDF files. Keeping PDF files as small as I can is important to me. If they're large and bloated, it makes my hosting costs higher and it's wasteful. I also provide puzzles to some newspapers and magazines. The media companies I sell to generally prefer vector formats, most commonly encapsulated PostScript, EPS, because it's part of their publishing pipeline. So I generate EPS files for those clients. If they want SVG, I give them SVG. So to recap, it's useful for me to generate raster files like PNG and JPEG, and it's useful for me to generate vector files like SVGs, EPS, and PDFs. There are tons of graphic libraries out there, and I've used several of them. PIL, P-I-L, which these days is installed as Pillow, is raster only. It's easy to install, it's easy to use, and I sometimes use it for visual debugging of my solvers. PIL has a built-in graphics class called ImageDraw, which is serviceable, although I don't like that it doesn't support changing the end caps on lines. It makes some of my puzzles, like Variety Sudoku, look bad if I don't use round end caps. See those bites taken out of the joints? Yuck. There is another render library called AGG, which works with PIL, which is supposedly better, but I don't particularly like working with it, and I don't think Python bindings support end cap selection either. Cairo, which supports both raster and vector graphics formats, is a good first choice. It used to be a bitch to install on Macs like 10 years ago, but it's currently pretty easily installed via pip and Homebrew. With Cairo, the same drawing code can be used to produce SVGs, EPS, PDF files, PNGs, JPEGs, all the ones I mentioned previously. And it also has proper endcap support. Yay! Cairo is what I'm going to use for this project. The other rendering library I use a lot is ReportLab. I use it to generate the PDFs for most of my puzzle projects these days. It has a few nice PDF-specific features that are missing from Cairo, but unfortunately it also has a different API for drawing, and also a different coordinate system. Most PDF-specific libraries, Y goes in the opposite direction from every other graphics library I use. For several recent puzzle projects, I've ended up writing a single context class that supports both Cairo and ReportLab. I mentioned earlier that I produce EPS files for newspapers and magazines. I could be using Cairo for this, but in practice I generate the EPS files without a library, outputting the CMYK EPS directly in Python. EPS and SVG are easy to read text formats, so why not? I like being able to understand exactly what is and isn't going in the file. Sometimes I need to make a series of images of the same puzzle being solved. For example, I might need it for a solving tutorial where I'm showing the solving sequence, and in that case I'll add a lot of features to the renderer to add different kinds of annotations and highlights to the puzzle. In this case, I'll often do some meta programming. It might be as simple as a shell script that calls a drawing script several times with slightly different parameters. A few times I've gotten fancy and made a little meta language for drawing sequences for tutorials. We won't bother here. I originally wrote my rendering scripts in Perl and used a PDF rendering library called PDF Reuse. I still have some scripts that use it, but I no longer write new scripts that use it because I no longer do a lot of Perl programming, and PDF Reuse, as cool as it was abandoned a long time ago, and it's difficult for me to constantly resurrect it. As I advance into my decrepitude, I've seen a lot of useful tools come and go. I really don't like revisiting code only to discover that it's now broken or I can't use it anymore. This is why I try not to adapt new tools that seem like they might not last long. It's why I don't depend on a library if I can avoid it. It probably contributes to why I'm more comfortable outputting EPS and SVG directly rather than using a library to do it for me. You can produce a Cairo renderer for these puzzles pretty easily. The solver here started out as a vibe-coded one, and then I just made a few tweaks. I've added this renderer to the Git repo. I also thought it would be fun to make a routine that draws pictures of lime, lemon, and orange cross sections. We'll use the limes for this puzzle and the other fruits for a future variation of the puzzle. To make the cross sections, I have 3 colors for each fruit, sampled from photos, which represent the peel, the pith, and the meat or flesh color of the fruit. Here's the code that draws the fruit. I draw a filled circle in the peel color, then a smaller circle in the pith color, then this ring of complicated wedge shapes at randomized angles. Then I add little radial fiber marks to the wedges and little stippling dots to the peel, which makes it look a little nicer. Honestly, I spent entirely too much time on this when you take into account that these things only appear on the answer page where they are super tiny. But later, I guess I'll reuse them for the interactive version of the puzzle where they'll be bigger. What's that I hear you saying? Just draw it with AI? Shut up. Look, I take some joy in actually drawing little pictures of fruit. And it's nice to know that little work went into these little tiny circles on the answer page. Okay, so I have some puzzle drawings, and I've identified which ones are potentially slightly easier. I'm going to load those into Photoshop and start solving them there and take some notes about solving strategies. Photoshop. There we go. There's puzzle number 2. I'll start solving these. In the next video, we'll be taking what we've learned from solving a bunch of these by hand and using that to rewrite our solver to solve more in the way a human does so that we can make better puzzles for humans to have fun with. I'll see you then. So let's see, this 3 here is going to suck up all the stuff, so there's nothing there, and there's 2 there. This is going to use all 3 there, so we don't use those guys.